In this lesson, we'll finish off learning target number 2, focusing on the combined gas law. It allows us to do calculations where the volume, pressure, and temperature change simultaneously. We'll also begin our discussion on learning target number 3, talking about Dalton's Law of partial pressure. Before we go on to the combined gas law, I want to introduce you to some terminology used to short form conditions for gases. Standard temperature and pressure, short formed STP, is code for a gas sample that's at 0 degrees Celsius and 101.3 kPa. Now, most experiments aren't done at STP. They're done at room temperature and room pressure. That's known as standard ambient temperature and pressure, or SATP, which is designated as 25 degrees Celsius and 100 kPa. This can be found in short forms in questions, so you need to memorize what these conditions stand for. Now on a quiz or a test, if you forget one of the values, one suggestion would be to make up a number, then complete the question. You'll only lose part marks for not having the right STP or SATP conditions, instead of leaving the question blank and not getting any marks at all. The gas laws that we've discussed so far in the unit are listed below: Boyle's, Charles, and Gay-Lussac's. Now they all have special conditions which don't make them always useful in real life. You can use Boyle's, Charles, and Gay-Lussac's law under carefully controlled conditions in the lab when you can keep what needs to be constant. Here is a summary of what each law stands for, what has to stay constant in order for the law to be valid, and what type of container you need to have the gas in. Very often outside of the lab, temperature, pressure, and volume can change simultaneously. In order to tackle these problems, the laws could be used step by step, like you did in practice problem number 20 for the assignment. A more efficient way to deal with that problem is to use the combined gas law. It's a super law that combines Boyle's, Charles, and Gay-Lussac's together to eliminate and remove many of the conditions that are necessary for the individual laws. Let's derive it in the space below. Volume is directly related to temperature. That was given to us through Charles's law, so V varies with T. Now, volume and pressure are inversely related. That's Boyle's law. So volume and pressure need to be in different spots. Because we have volume in the numerator, we'll put pressure in the denominator on the opposite side. Now, temperature and pressure are directly related as well. This is shown in the proportionality statement by having the variables on the same side but in different locations, one in the numerator and one in the denominator. If volume stays constant and temperature goes up, then the pressure has to go up as well in order to keep this fraction equal to the same amount. Now let's change this proportionality statement into a math equation. When we do that and introduce an equal sign, we need to put in a constant to fix the relationship for a real gas. Because this is the fourth gas law, the constant's known as K4. Now, we don't want to have to look up the combined gas law constant for each gas we're using in a question. So let's do our math trick in order to eliminate K4. Let's say we have a balloon with an initial temperature and pressure. We'll call that V1, T1, and P1. And then we change the temperature by heating it, and then we also squish the balloon under water, increasing the pressure. Now we have final conditions. We'll call those V2, T2 and P2. Now K4 is the same, and it's the same value because we didn't open the balloon and change the type of gas that we have. I can rearrange these equations so it says K4 equals. For the initial conditions, it would equal P1V1 over T1 equals K4. For the final conditions, it would be P2V2 over T2, which also equals K4. So I can eliminate the K4 and make those two equations equal to each other. This is the form of the combined gas law that we're going to use. Now there are still a couple of conditions on it. Temperature must be in kelvins, and the amount of gas needs to stay constant. But we can use this equation if any of the external variables on a gas change, and also if we're in any type of container. It's called the combined gas law because you can see each gas law inside this formula if you cover up what stays constant. For example, Boyle's law, temperature stays constant. So if we cover it up, you see P1V1 equals P2V2. In Charles's law, pressure stays constant. So if we cover up the pressure, you get V1 over T1 equals V2 over T2. And in Gay-Lussac's law, volume stays constant, and P1 over T1 equals P2 over T2. Let's try out an example using combined gas law. Now these examples have lots of numbers given to them. Because we've got a math equation with 6 terms in it, you'll be always given 5 numbers and expected to rearrange for the 6th. Now be careful, some of the numbers can be given to you in the abbreviation STP and SATP. Example 1 says, in the morning, Judy puts 2.5-liter balloons on her mailbox as part of her son's birthday. Then a high-pressure system moves in, or 104.9 kPa, making the day sunny and 32. Those are final conditions. If the morning air temperature was 15 Celsius and the pressure was 101.3 kPa, what will the volumes of the balloons be? Let's plug in what we're given here. Our initial pressure in the morning would be 101.3 kPa. At that pressure, the balloons were 2.5 liters. And the temperature was 15 degrees Celsius, which is 288 Kelvin. For final conditions, I know P2, it's 104.9, and I'm asked for the volume of the balloons, V2, and the final temperature is 32 degrees Celsius, or 305 Kelvin. To solve the question, I need to isolate V2. Now there's, again, a couple of different ways that you could do this mathematically. Some people like to simplify this fraction and then times by 305 and then divide by 104.9. I like to type this all into my calculator and just hit equals, and it works it out for me. So I'll type in 101.3 times 250 times 305 divided by 288 and then divided by 104.9. V2 equals 2.5567. Now for sig-digs, I can keep 3. I have 3 in my volume and 3 in each of my temperatures. So the balloons will be 2.56 liters. Today we'll also discuss Dalton's law of partial pressure. It's a very straightforward law to wrap your head around. It deals with mixtures of gases and states that the total pressure of a mixture of gases is the sum of the pressures of each of the individual gases. This is represented through this equation. The dot 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 means you just continue until you run out of pressures for the ingredients in your mixture. Example 2 shows you a direct Dalton's Law question. If 3 atmospheres of CO2 is added to 2 atmospheres of chlorine, what's the total pressure of the container? If you simply sub in the numbers that you're given, P total is going to be 3 atmospheres plus 2 atmospheres. That gives us 5 atmospheres. And I can only have one sig dig on my answer. An application of Dalton's law of partial pressure is working out things in percentages. We know that air contains 78.0% nitrogen gas at STP. Remember, STP is 101.3 kPa and 0 degrees Celsius. Here we're asked to calculate what the partial pressure of nitrogen is. That is nitrogen's contribution to the air pressure. The total pressure of air is 101.3 kPa. Because air is 78% nitrogen, if we times our total pressure by 78% expressed as a decimal, that will give us how much nitrogen contributes to the air pressure. I can keep 3 sig digs in my answer, so I'm going to round this to 79.0 kPa. Complete the combined gas law and the Dalton's Law questions listed on your Unit 5 assignment cover sheet.